All right, I have to lose the half of it. Apologize for those of you who watched the recorded video. Contact me if you need more clarification on these notes, okay? So 2.9 inch square multiplied by 60 KSI divided by 0.85 and multiplied by 4 KSI and multiplied by B, which is 14 inch, okay? All right, so now I got is A equal to 3.66 inch. A equal to 3.66 inch. Okay, so I want to make a quick pause here. I apologize for not recording the first like 10 minutes of the lecture. And what we did is we record all we did from last lecture till we reach the apply moment at the middle span of the simply supported beam. And we introduced a new concept called tension control reinforcement limit. And this is a reinforcement ratio where my strain steel reaches to be 0.005. And we use that equation and arrive at a ratio for reinforcement area, calculate that reinforcement area, bring back in to calculate the effective compressive zone. And carry on with this effective compressive zone, I now obtain my moment capacity and giving you and want to notify that this is basically MN1, okay? And I'll explain why. But I can calculate using ASTC Fy, and this is essentially just the tension force, okay? And ds minus half A, that is the lever arm or distance. So 2.9 inch squared multiplied by 60 KSI multiplied by a 11.5 inch minus A is 3.66 inch divided by 2. And I got this number MN1 equal to what? 1683 kips inch. All right, and I want to divide that by 12 to give me a kips foot. So I got 140.25 kip foot. Okay, so this is a good number, and I already know it's tension controlled, isn't it? So I can say phi equal to 0.9. Phi equal to 0.9. So with this, I say phi mn, and don't forget this is phi mn1, okay? And that equal to 0.9 multiply 140.25 kip foot and arrives at a 126 kip foot, which is much less than the required, much smaller than the required, which is 166 kip foot. Okay, so what happened? What happened here is that design as singly reinforced section did not work. Did not work. Why? I end up with a capacity much less than the required capacity. All right. So at this moment, some of you may start jumping, say, look, Bob, you're wrong. It might work. How can I make it work? You know, you take a look at the section. You take a look at the section, and this is a square, right? All you did is assume you have provided enough bars, about 2 point, what is the area of steel? About 2.9 inch squared, okay? That is how much I provided. So to be precise, 2.9 inch squared is equal to 3 number 9 bars, isn't it? Or if I assume number 8 bars is about 4 number 8 bars, isn't it? Okay, let's just leave this doubt whether I can, whether I can fit in this 4 number 8 bars within this very short 14 inch of a width or not. Okay, let's just say we can fit in. And even if you fit in at this point, you say, you know what, I'm going to increase the steel, right? So what you want to do is put another layer of steel, for example, to increase the tensile reinforcement area, then to gain more moment capacity. So what happens? What happens that, yes, indeed, you increase AS, right? You increased the T, which is AS Fy, okay? But you need more A, which is compressive zone, to increase or to balance, precisely to say to balance. Why? Because you need the C, compression force increase as well. So you end up with a problem because now the compression force might cover the tension area. You say, why, Bob? How do you know? You haven't fit in yet. I know that because the height is so short. It's only 14 inches. It's 14 inches. Okay, so simply said that 2-layer or multiple layer, in this case, 2-layer steel wouldn't work. Okay, wouldn't work. And that justifies the reason why we cannot design as a singly reinforced section. So you might already yield at the conclusion that seems like for a stocky section, means short and wide section, not likely to work with singly reinforced case or singly reinforced design. Okay, just not enough room, just not enough room. All right, so what we do instead, doubly reinforced design is preferred. Okay, so we end up with a design that I can put 2 rows of bars, and this is still assuming I can put 4 number 8 bars, which still need to be checked. But anyway, number 8 on top and on the bottom of the section, on top or on the bottom of the section. Okay, all right. Okay, so this is our task now. So we're going to redesign to find the added moment Mn2, or should I put this 2 on the subscript here? Okay, all right, so let me start another page and carry on. So number 4, step 4. Okay, so that is find out additional moment resistance. Okay, again, when you see this basically is flexure strength. Okay, is needed, right? Oh, sorry. Find out additional flexure strength needed. Right? So this is not too hard to do. Okay? How do we do that? So Mn Tc, or we named it as Mn1, right? Equal to what? Equal to 100, where is it? 40.25 kip foot. But let me just convert everything back to kips inches, and I'll tell you why shortly. Why? Okay, and this is 16A3 kips inch. Okay, which is smaller than Mu, which is 2, and I convert that back. This Mu is 166. I just multiply 12, and this gave me 2,013 kips inch. Okay, and now Mn2, which is added, right? Which is added. Okay, so this is Mn2, by the way. Is additional moment required, right? Need to be Mn, right? Sorry, Mu. My U looks like an N today. My Mu, okay, minus Mn Tc, or Mn1. Sorry, I have 2 systems. It's confusing here. Okay, so I end up with 2,213 minus 1683 kips inch. Okay, so that leaves me behind with 530 kips inch. So that, ladies and gentlemen, is additional requirement. Okay, so with this, I know I need additional moment resistance or flexure strength of 530 kips inch. And the reason why I converted everything back to kips inch is because I will end up finding the area of steel in terms inch squared. Okay, so with this, let's observe the structure, right? Let's observe the reinforcement. Okay, I know it's going to be 4 number 8 in the bar, but I'm just going to be lazy. I say this is AS. Just one lump of steel together, just one layer, okay? And this is AS prime. All right, and let me, Yes, ma'am.
Where do you get the 2, or I guess 2,213? Because when I did 66 or 166 times 12, I get 1,992.
Sorry, I forgot. Divided by
Oh,
0.9.
okay.
Yeah, because this should be mu divided by phi. I'm sorry. Do you get it better? I mean, do you get this number 2213? Let me quickly check. I did this number
Yeah,
last night. You
I
got
did
it? All right,
get
thanks.
that. Yes.
Sorry about that.
Yep.
I went too fast. Thank you. For the correction, this should be divided
Yep.
by phi here, okay? Guys, all right? Okay, so now this is ds prime, since that's a spacing for the compressive reinforcement. And this is ds. Sorry, I wouldn't say ds, but this is ds. This is ds, okay? And then I want to draw the strain diagram, right? So first of all, always draw strain diagram. So I line up the top and bottom line here, and I draw epsilon Cu equal to 0.003, okay? And then I draw a straight line inclined to reach here, and this is epsilon S, and this is epsilon S prime. Okay, and don't forget I have a actual compressive zone C here, not effective, not effective. All right, but just to put myself in a very clear position, C should equal to A, which is effective, divided by beta 1. Okay, C should equal to A divided by beta 1. And C then A, what is A? What is A, right? We assume, right? Let's assume, let me put down here. So if you write that, don't worry, you can keep writing, but let me just say, assume A stays at previous calculation. What is my previous A? If you scroll up here, it's 3.66. So let's make assumption that A stays at 3.66 inch. So C equal to 3.66 inch divided by beta 1. And we know beta 1 0.85 for F prime C for KSI. So C eventually equal to 4.3 inch. Okay, 4.3 inch. All right, so now let's move on, right? Why do I need to know that? Why do I need to know that? Because what I need to find out is that I know mn2 equal to the as prime fs prime. As prime fs prime. What's that? That is the compression force by steel. All right, compression force by steel. And multiply the distance, which is ds, because we're summing the moment. We're summing the moment to with respect to the bottom steel here, okay? So ds minus ds prime. Okay, we already know mn2 by previous calculation, right? All I need to find out, right, is the rest of them, which means I need to find out this, I need to find out this, then I can find out as prime. Remember, because the goal is to find out the compressive reinforcement needed to withstand the moment applied. Okay, so that's just my thought process. Okay, that's just my thought process. So you don't have to write down like this, but I wrote it down here. So just to show you that this is my thought process. Okay, all right. So with the C calculated, I can find Fs prime now, which is compressive stress in the compressive reinforcement. And that equal to the Young's modulus of steel multiply epsilon S prime. And that equal to, using the similar triangle, epsilon Cu multiplied by C minus ds prime divided by a C. Okay, so Fs prime equal to, bring the number ES, Young's modulus, which is 29,000 KSI for steel, and epsilon Cu 0.003, and C, which is 4.3 inch, minus ds prime. We don't know ds prime, isn't it? We don't know. So we can assume, if you are not given, assume ds prime equal to 2.5 inch. Okay, so 2.5 is a magical number. I use that a lot because a lot of cases we can use it for different number. So 2.5 is a good number to remember, okay? 2.5 inches of concrete cover divided by 4.3, which is the actual compressed zone C again. So Fs prime end up being 36.8 KSI, okay? And then I can calculate AS prime using that thought process I just talked about, okay? So AS prime now should equal to mn2 divided by Fs prime and bracket inside ds minus ds prime. All right, so now let's bring the numbers in. So AS prime equal to mn2. What is mn2? Remember, 530 kips inch. I kept the unit to be inch. So 530 kips inch divided by Fs prime, 36.8 KSI, and divided by ds, 11.5 inch minus ds prime, 2.5 inch. Okay, you went through the calculation, you realize that AS prime is just 1.6 inch squared. 1.6 inch squared. If you are so smart and you realize immediately, you know what, that's just two number 8 bars. It's two number 8 bars. Why? Because each number 8 is 0.79 inch squared, right? And multiply 2 roughly equal to 1.59, right? Sorry, 1.6 inches squared. Okay, a hair less, okay? But regardless, right, we can carry on. So once we find out this is required for the compressor reinforcement, we move on to the next step. Okay, so next step is select the bars. Okay, select the bar. So did I miss a step? I believe I missed a step. So
Yeah,
find additional moment, right? So sorry
yes.
about that. Let me add it here, okay? So you don't have to worry about it in your write-up. If you write on the paper, just add it here. So this is number 5, find AS prime. Okay, sorry about that. So once we got AS prime, we can select the bars. All right, so things got a little bit tricky. Okay, why? Because you take a look at, I need AS prime to be 1.6 inch squared. All right, although I just wrote down here 2 number 8 will do the trick, but you know what? Just for the sake of clarity, let me remove that because I haven't selected the bar yet. You can keep it, but just for my sake, I want to remove it for now, okay? So I'll say AS prime equal to 1.6 inch squared. AS, from previous assumption, tension controlled assumption, that equal to 2.9 inch squared. Okay, now this is going to cause me problems. Why? Remember, when I arrive at this number, I assume it's tension control. That means the phi equal to 0.9. Matter of fact, the whole thing was done under the assumption that it's tension controlled, phi equal to 0.9, isn't it? So that's a little bit much. Okay, and now I also realize that this AS prime is a compressive reinforcement. That means if I put a section here, and this is a concrete section, I'm gonna put 2 or big chunk of steel in it. Okay, if I put a big chunk of steel in it, I have to lose concrete. What happened? I put a bar in and dig a hole of concrete out, dig a chunk of concrete out. So that's not gonna do it. So I have to do a conversion first. So what conversion? I need to do AS prime corrected. Okay, why corrected? Because I need to account for the loss of concrete, which is AS prime multiply FS prime divided by FY. Okay, and that is 1.6 inch squared multiplied 36.8 KSI divided by 60 KSI. Unit cancel, so I got 1 inch squared. Okay, so this is what I have for correction. And now the total still require AS. Let me say total. Okay, that includes the tensile reinforcement AS and AS compressive corrected. So the total reinforcement needed now equal to a 2.9 inch squared plus 1 inch squared. And that is 3.9 inch squared. Okay, So this is actually the tensile reinforcement needed. New tensile reinforcement needed. Okay. If you couldn't understand this, that's fine. Work through it for now. Remember it, and we can explain this in detail later. Okay. But the procedure goes, this is the tensile reinforcement. Okay. And now the compressor reinforcement stays AS prime equal to 1.6 inch squared. I did not change a hair. Okay. Now with this, I would say at the final design, okay, I will need a tensile reinforcement, okay, tensile reinforcement of 3.9 inch squared and a compressor reinforcement AS prime of 1.6 inch squared. 1.6 inch squared. So that is the final design. Okay, are we done yet? Not yet. Not yet. Why? Because now we need to select the bars. Now we need to select the bars. Okay, so I need AS, which is tensile reinforcement at the bottom here. So let me just remind you that we end up with this tensile reinforcement at the bottom here. Okay, equal to 3.9 inch squared. And I need this to be AS prime has to be 1.6 inches squared. Actually, larger or equal. Okay, so I want to fit bars. I'm going to select.
I got a question. Is that a AS, not 2.9 inch square?
Where? Here? Here?
The one on the bottom.
Here? Sorry.
Yeah.
Let me clarify for you. It should be greater or equal than. Better? Greater, equal than. Clear?
It wasn't 2.9 instead of 3.9.
It was 3.9. Okay.
Oh.
So you missed the, we added for the loss for concrete. Okay. Like I said, for now, follow this procedure and let me finish this and we can come back explain what's happening here. Okay. All right.
Yeah, I got it.
Yeah. Okay. No problem. Yeah. I don't want us to come back and forth on this. Okay. So now I know it's 3.9 for tensile reinforcement and 1.6 for compressive reinforcement. Okay. I need to select bars. So I'm going to select 2. Okay. Number 9 bars. All right. Or, sorry, I can, should I say, change this. It says assume number 8 bars, right? So I can select either 4, which 4 divided by 0.8, so 5, number 8 bars, okay? Or I can select 4, number 9 bars for AS. Okay, same thing here. For 1.2, I can select 2 number 8 bars, just a hair less, or I can select 2 number 9 bars for AS prime. Okay, so now we said assume number 8 bars. So you can either go with this or you can either go with this. I eventually, after weighing the number of bars, one less bar to consider, I will go with this design. Okay, this design. All right, so that is the designing process. That is the designing process. Okay, now, once I select the bars, what I will do, I will go back. Okay, so this is probably step number 6, this is number 7. Check MN phi again. And why is that? Because now I end up with a section that has a width of 14 inches, height of 14 inches. Okay, but with 4 number 9 bars. So 1, 2, 3, 4, and you can check in table 5 to see if you can fit in or not. My theory is that it will work. Okay, and then I have a 2 number 9 bars at the top. Okay, and regardless of the arrangement, I have a cover of 2.5 inch. And assuming it's one layer now, I have a 2.5 inch. And I can recalculate the section. Okay, how do I recalculate the section? How do I recalculate section? I need to do the doubly reinforced basically analysis of doubly reinforced section. Okay. All right. So I'm going to stop here and leave this part 7 to Monday. Okay. But let me circle back to address this mysterious part. All right. That's where Sergio is asking. So now take a look here. We went all the way. We went all the way, right? By assuming singly reinforced case to doubly reinforced case, and find that I just need additional AS prime equal to 1.6 inch squared. Okay, so why I do this? Okay, there are two reasons, right? Why is that? One is that I lost the concrete, and second is that I add this AS prime was not there before. So when I do tension equal to compression, right? Remember when I do tension equal to compression, I added more compression. I need to add tension back up to balance it. All right. So that is the reason why I convert this to be AS from AS prime to be AS prime corrected, because this is essentially the stress in the compressive side of it and the stress in the tension side of it. This is Fy, this Fs prime. Okay, because they're in a different stress state, so they're not a one-to-one conversion. So I need to add this one as a corrected version because I have to add this amount to the tensile reinforcement to balance. All right, so after that, I end up with an increased, okay, with an increased, let me take this color out, increased tensile reinforcement. Okay, because the conversion. All right, now you don't have to do all this. Matter of fact, you can go from here without doing the conversion and jump right in to select the bars and jump right into the analysis of the section. But you end up having to do this when you do an analysis because you will find it very hard to have a tension compression balance there. All right. If you don't believe it, try it yourself and come back with answers and we can discuss. All right. So the way we did here by adding this replacement, it will eliminate additional troubles when later you're trying to balance the tension and compression forces. Okay. All right. I'm going to leave the last step, like I said, until Monday because I want to give a little bit of review on the upcoming exam. Okay. So I want to stop here, pause here for a second. Do you have any questions for this so far? Folks, anything? Anything?
I don't have any questions on this particularly.
Okay, I am going to upload the homework number 4. You will be able to solve first part of it, but you won't be able to solve the last part of it till Monday. Okay, but homework number 4 shouldn't be that long. All right. Okay, so let me just stop here, pause here, and we can continue on Monday on this design of doubly reinforced section. Okay. All right, so let me pause here and show you what I think will happen for the exam. Okay, so review. Well, actually, I can keep going using the same board here. All right, so exam number 1, review, right? What we have talked about so far. Okay, so let's list all of the content that we cover. First, we talk about the properties, basic properties. Of concrete, steel, okay? And for concrete, right, what it looks like, we use stress strain curve, right, to represent or describe the behavior of concrete, right? Remember? And so for compression side, it goes like this and drops and fails. For tension side, it goes like this and drops and fails, okay? So we call this right here at the peak stress is FC prime, okay? F prime C, okay? And then we call this Young's modulus of EC, which is 57,000 square root F prime C, okay? Or you can use the density of concrete to calculate that, right? So remember all this, right? And then we also said, look, here at failure, right? At failure, epsilon Cu equal to 0.003, right? We need to remember that, right? And now here we have Ft, which is tension side or tensile strength of the concrete. And that roughly equal to what? 7.5 square root of F prime C. Now, why do we need that? Because we also call it modulus of rupture, and we use it to calculate the cracking moment. How do we calculate the cracking moment? You can go back to the notes and figure it out. Okay, all right. Now you can keep writing, but for me, I just want to save some space so I don't have to scroll too down. I'm just gonna move here a little bit. Okay, for the steel, we talk about it as well, right? Let's observe the stress strain curve for steel. Okay. Now, left-hand side is concrete, and this is for steel. The main difference between steel and concrete is what? Is the symmetry. So for steel, it is symmetric. And it both yield in tension and in compression the same strength of Fy. Okay, same strength and Fy. And this Fy here equal to the grade of steel. 60, 70, right? So what does 60 mean, right? So Fy 60 means 60 KSI, right? 75 KSI, so on and so forth. And most important thing is that we talk about Young's modulus of steel, and that number, like I said, should be drilled into your head already, 29,000 KSI. Okay, so that is very, very important. Okay, now another thing often omitted by us is the yield strain of the steel here, which is epsilon y. Okay, so I keep saying that, and you probably already remember the number epsilon y equal to 0.00207. But this is only for grade 60. Be careful. Why is that? Because epsilon y should equal to Fy divided by ES. For example, for 75 or grade 75, what you have, epsilon y 75 equal to 75 KSI. Young's modulus still stays 29,000 PSI. Okay, so sorry, 29,000 KSI. Okay, so you can go ahead and calculate, find that strain, and that is not 0.00207. Okay, so this is as much we're going to talk about the basic property of concrete steel in terms of behaviors. However, though, we do want to talk a little bit about test of concrete cylinders. Oh, sorry, test of concretes, right? So what we use for compression, from your homework, you already know it is either 6x8 or 6x12 or 4x8 cylinders. Okay, and I really prefer to see English unit or US system, right? I don't want us to use 150 millimeter cube anymore for it, so it's always going to be 6x12 or 4x8 inches cylinders. Okay, and for those of you who are a little bit interested, we need at least 5 to 6 cylinders for 4x8, at least 3 to 4 for 6x12. Okay, sorry, 6x12, 3 to 4 number of cylinders. And if you were to get ACI field testing technician certificates, which I had, that you go through how to use wheelbarrow and shovels to fill perfect cylinders, okay, and cap them properly. All right, but for the exam purpose, we need to know that these cylinders will be tested 7 days, okay, 21 days, sometimes, and 28 days. Okay, now for all intent and purpose, if in the exam time, I want you to test the cylinders, 28 days is always the final number, right? Why is that? Because 7 and 21 days are the early strands. This is called early strands. Okay, and this is the normal case, right? Normal. So 28 day is the time we use to crush the cylinders. And so as the split cylinder testing for tensile. And if you were to use this, and this is what we call FCT, okay? And also for beams, like so. And this is FT or FR, modulus rupture. Okay, be careful. All right, so these are something we covered. And then we also covered the Whitney stress block. Okay, remember how we talk about it? I'm gonna go super fast now. And analysis of singly reinforced section. Singly reinforced section. Analysis, okay? Analysis. And analysis of doubly reinforced section. Analysis, okay? And design only singly reinforced section, okay? Design only singly reinforced section. And that is given section geometry, okay? Given section geometry, okay? All right, and last but not least, bar detailing. Meaning bar spacing, remember how we place the bars. And most important case, if you remember, we showed the stirrups. How do you get the spacing? How do you get the clear cover? So on and so forth. And that, ladies and gentlemen, is all we're gonna cover in this exam. All we're gonna cover in this exam. Any questions? Folks, any questions?
I think we got it.
No, Professor.
All right, good deal. So now let me give you the secret, right? So this is the sauce we're all waiting for, is what the past exam looked like. And it'll only take you 5 minutes, I promise you. Which you probably want to take a little bit more, but anyway, sorry, okay. So now, can you take a look at the screen here? And let me warn you, no screenshot is permissible, okay? Don't take screenshot. And this is last year's exam by Dr. Sneed and I, our session. And I can assure you this same problem won't show up in this coming exam. That's why I feel so comfortable of sharing this with you. But I just want you to take a look at what type of problem you'll be facing, right? So first one, short answers, 25%, okay? Let me read out the first problem to you. The stress distribution in a concrete compressive zone, compression zone used for flexure design in accordance with ACI 318 code can be represented by equivalent rectangular concrete stress distribution. That is Whitney stress block with a height that and a magnitude that. So the height is what? Dependent on F prime C, because we need to determine beta 1 value, remember? And the magnitude means the strength, which is 0.85 F prime C, okay? So C will be the correct answer for this, okay? Number 2, the compressive strength of concrete is determined by means of what and tested in accordance with what. Means is method, right? So which method? We're talking about compressive, so I just talked about it. Cylinder loaded in the cross-section with uniform pressure on the cross-sectional surface of the cylinder. Yes. C39, yes. So either gonna be A, because I see 39 here, or E, right? Take a look at the E. Cylinder loaded on their side with uniform line loading along the length of the cylinder. This sounds more like a split tensile tester of the concrete. So I'm not gonna pick E. The correct answer should be A. The correct answer should be A, okay? All the other have wrong ASTM numbers, so no. Number 3, which of the following statement is true? A, the yield strain of reinforcing steel in tension is higher than the yield strain in compression. We just said they're symmetric, so nah. Number B, the yield strength of reinforcing steel in tension is higher than the yield strength in compression. Nah. The modulus of elasticity of reinforcing steel in tension is higher than the modulus of elasticity in compression. And then again, no. The stress-strain relationship for reinforcing steel in tension is the same as that in compression. Bingo. So D is the correct answer. Okay. 4, the purpose of strength reduction factor phi is to account for what? All right, pay attention. Now, we didn't talk in length of this. Okay, but let's take a look at the answer, right? So where the purpose of load factor is account for what, right? So phi is account for what? Under strength of member, yeah. The variation of load during the lifetime of the structure, yes. So I think A is a possible answer because phi is considering the uncertainty of the materials and properties of the materials, yes. So undermine the strength of member. And the factor is to amplify or exaggerate how much load. So A seems to be a good answer, right? But let's go on. B, the under strength member, yes, a load inaccuracy of the design equation. Now we know exactly how much load we're putting on the structure, right? So no, not B. C, the importance of the member of the structure. That sounds more like it. That sounds more like it. On the under strength, yes, but this is importance. Why? Because we see the tension control limit. Is that right? So those are a little bit different now. So C might be the right answer, but let's take a look at the latter one. Errors made for using wrong materials properties. Nah, there's nothing to do with load factor. So I'm not going to select C. D, the importance of member in the structure. Sure, construction error. Oh, come on, forget about it. If I'm going to know I have a construction error, I'm not going to design properly, right? So apparently A is the correct answer. Okay, so that is the understanding of phi and factor loading. Okay, all right, moving on. Number 5, consider the beam with a cross section shown below. The beam is in positive bending with F prime C is 7,000 psi, Fy is 60,000 psi. The concrete is normal weight. Okay. Now the cracking moment RC section is the cracking moment. How do I calculate cracking moment? I use modulus of rupture and I use the section properties. Remember that equation? If you forgot, go back, right? I can quickly calculate these numbers. Okay, now effective depths of D, what are we trying to ask you? What we are trying to ask is the center of the bottom of these group of bars, okay? You find that, use height minus that, you get your effective depths. Number 3, if the maximum aggregate size is 1 inch and the beam is a part of floor that not exposed to earth or weather, the calculated minimum beam width is what? All right, so the first half of the sentence clause says the maximum aggregate size is 1 inch. Where did we use the maximum aggregate size? Bingo, I remember it is determining the spacing between bars, right? Okay, so use this number, I can determine the spacing between bars. All right, second, what is a part of floor that is not exposed to earth or weather? Remember that is in the table ACI 20.5.1.3.1, where there's for non-pre-stressed member not exposed to earth or weather, there's a concrete clear cover stated. So I can use the right clear cover, okay? Now, looking at the section, right, is asking what is the minimum beam width. So I'm looking at the minimum beam width here, which is 14 inches given, but what is the minimum number? So how do I calculate? I do the spacing of these clear spacing and bar spacing, bar size, and get this number calculated. And if you're lazy, you see what? I'm gonna use table A5. Good luck. Because you find the table A5, we provide none of these numbers for you, okay? You actually have to do calculations, okay? So you can use your table A5 to do a check because table A5 is gonna be bigger than the calculated number, but still try to calculate yourself, all right? If you don't know how, email me, okay? All right, so that's problem number 1. It's not difficult, right? It's rather lengthy. Number 2, the reinforced concrete beam has a factored moment diagram. Notice here, I already saved you time. It's factored. You don't have to do any factor after all, okay? And the concrete is normal weight, unit width is this, and strength is this, and yield strength is this. How to solve this problem, right? Since the factor moment, meaning the live load PLL, the dead load omega DL, all these has been considered, meaning you don't have to do any structure analysis, okay? So you just use this number as apply moment. MU 450 cubic foot, that's it. Okay, so first problem, determine the nominal flexure strength MN, okay, of the AA reinforced section. These are keyword, okay, for positive bending, okay, for positive bending, meaning this is in the middle span, positive bending, okay. That means bottom bar 3 number 10 in tension, top bar 2 number 9 in compression, okay. Include the effect of compressive reinforcing in calculation, of course. And if the iterative procedure is used, perform these 3 iterations in your calculation, show all your work. Remember that change of compressive zone C, before we select somewhere 3 over D, there's a D over 3 to D over 4. We pick a number, run through the equilibrium, trying to determine whether the tension balances the compression. If not, we change the C number again, redo that. If not, change the C number again, redo that. Remember? Yes. So that has to be done 3 times at least, okay? 3 times. And the difference between the tension and compression is required to be less than 3%. If you come up short, say 5%, 10%, and stop iteration, sorry, still have to deduct points, okay? Got to control it with 3%. To B, determine the value of AS min. Remember the equation? 3 square root F prime C BWD over Fy, 200 BWD over Fy, remember? And verify whether the reinforcement provided meets the minimum requirement, right? So show all your work, okay? Just a comparison. Now, determine the value of phi strength reduction factor and verify whether the design flexure strength is adequate to resist the loading. What we're trying to do, phi Mn compared to Mu, right? Is it bigger than equal to or otherwise? Okay, last problem and last minute. Problem number 3, design, okay? So cast in place reinforced concrete beam shown below. Empty section, nothing is given, but cast in place, I can go in table, ACI 20.5.1.3.1 non-pre-stressed member concrete clear cover to find the concrete cover first, okay? And the maximum factor moment Mu and the cantilever portion has been determined to 450 negative bending. All right, when you see negative bending, you know that my bars in the section has to be in the top if it's singularly reinforced, okay? Why is that? Because the tension is in the top if I have negative bending. Okay, now assume F prime C is 6,000 PSI. It's now 4, okay? It's now 4. So you have to change your beta 1 value, okay? Fy equal to 60 KS, that's 60,000 PSI. Maximum aggregate size, again, you know the bar spacing now, didn't you? And the shear reinforcement consistent number 3 stirrups tells you that already. The beams inside a trium or hotel building means no exposure to weather. So choose the concrete clear cover properly, okay? And then say design for section A. If the beam width B is restricted to 16 inches, tell you that design the rectangular section in section A. You need to determine the height. How do we determine the height? You have the span length divided by the corresponding number per the note. You get the height to start with, okay? And then say single layer reinforcing bar in tension zone, okay? Single layer reinforcing bar, singly reinforced, single layer, simplest the case, okay? Meaning about 2.5 inch of concrete cover, check, okay? Height of beam should be an integer values. The total height, you may have to choose an integer, okay? You do not need to revise the moment for the self-weight, meaning self-weight is included in this negative 450. Don't have to do any structure analysis, okay? Only number 10 bars may be used for the reinforcement. We fixed the bar size, so all of you guys should come up with the same or similar design, okay? Now, each individual problem set will be slightly different, so want to focus on your set only, okay? Assume that the centroid of the reinforcement to be 3 inch from the extreme tension face of the cross section. Now, here's a trick. What do you mean by extreme tension? It is a negative bending moment. All right, folks. So the tension's on top instead, okay? Tension's on top. So when we say extreme tension phase, that means the top line right here. That is the extreme tension phase. If it is a positive moment here, then when I say extreme tension phase, it will be at the bottom. But fortunately or unfortunately, we have a negative bending here, okay? All right, so determine the phi Mn, perform all the necessary code checks for the reinforcement selected, show all your works, okay? All right, last, draw the reinforcement obtained from problem 3A in the cross section, label dimension, reinforcing steel bars properly. What are we asking you? We're asking you to calculate the required steel, select the bars, come up with a moment that adequate to resist the applied moment. Then at the end, draw the location of bars and place the stirrups accordingly and label the concrete clear cover properly. Okay, and ladies and gentlemen, we're done. That is last year's exam. Okay, now I may give you a full problem, but it will be the same level of difficulty and the length of time takes for finish the exam like last year. So any questions, folks?
Nope.
I don't know if this is already asked, but how many homeworks are we going to have graded before the exam?
I will be finishing number 2 by tonight. That is once you submit it. And if further delay, that will be tomorrow morning. And each individual you will receive a specific comment on the problem. I think you did horribly. So you just have to review that problem only. Okay. And
Okay,
regarding
thank
the home, yeah, sure. And regarding homework number 3, I'll try to get that done by next Tuesday. I have to travel over the weekend, but definitely Monday I'll be back, and Tuesday I should be able to finish that. So if meantime you really need to review the content and feel like you want to get the answer from homework number 3, email me and we can set up individual meetings. All right. Okay. Anything else, folks?
I have a question regarding problem 3 on homework 3.
Yes, sir.
Yesterday, I think you gave some clarification about the problem, and it had to do with the clear cover.
Yes, sir.
I think you said something about it being 2.5 in problem 3. Is that correct, or
Yes.
did I misinterpret?
No, you're right. I just said 2.5. You can use that number for the homework purpose.
Number 2 said that the clear cover was 2 inches. Should we use 2 inches for that one?
Sorry, if it's given, if it was given by the problem, use whatever is given. If it's not given, use 2.5 throughout.
Okay, thank you.
Yeah, not a problem. Any questions, guys? Anything else? Okay, I just want to provide one word of wisdom since we're all here, and for those of you who are watching the recorded lecture later, the first exam is very important, and you want to start reviewing right now. Okay, and I have Tuesday office hour from 2 o'clock, and I will be there. So if you have any questions, and there's no simple or what's this question, any question is good. Just ask me through the office hour or send me email. I'm very good at responding email. Okay, so if you send email, I definitely reply. Even if I don't know the answer or say I don't know the answer, I reply to you. Okay. All right, folks. Okay, now one thing is about practice. If you run out of materials to review, say if you've gone through all the homeworks and you feel confident about it, you can practice on chapter 4 and chapter 5 in a textbook. There are assignments and problems behind those. And if you practice those and you want to compare your solution to the answers, you can let me know and tell me exactly which problem you need answer to and show me your work, and I can send the solution or I can discuss the solution with you, okay? All right, I'm gonna stop recording, but